Okay, let's talk a little bit more about flow regimes now. Once this small module is completed, you should be able to describe the difference between laminar and turbulent flow, be able to relate these descriptions to flow of drilling fluid through varying geometry and with varying fluid parameters, and understand the significance of the Reynolds number and how to relate that to flow regimes, and consider the effect of the flow regime on the well being drilled as well. So in any dynamic fluid environment, two distinct flow regimes can actually be identified, and that's laminar and turbulent. What do we mean by laminar and turbulent? Well, if you actually have a look at this picture of some water as it kind of slowly flowing over, it's fairly shallow here, it's flowing relatively slowly, and then as it comes into a deeper area, it's changing direction and speed and so on, and it's becoming turbulent. Basically, it's becoming more chaotic over here. So there's basically straight parallel lines in this picture on the in the left-hand side of this picture, and there's just basically chaos on the right. But there are still some common, there's still some common things. I mean, both of them have a velocity in this direction. There's still a flow from left to right on the photograph, but one of them is, as I said, parallel, and one of them has a whole load of different directions within it, but an overall flow direction as well. So what's actually changed between the left-hand side and the right-hand side? Well, the geometry has changed, as in here it's shallower than here. This is deeper, so the depth of the fluid has actually changed. And the direction of the flow has also changed. The individual direction of flow, as in it's pouring over here into a deeper channel, if you like, and therefore it's actually beginning to start turning on itself and going in a more chaotic manner. But as I said, overall there's still a constant direction of the overall fluid as it flows over this weir here within the river. Other types of fluid which can exhibit the same sort of thing, laminar and turbulent flow, are things like smoke, or gases. It can exist in any fluid basically, but to demonstrate it we can actually have a look at some smoke actually moving if we move on to the next slide here. Now if you have a look at this, we've got a little joss stick burning in the bottom here and some smoke coming off of it. And if you watch this, you'll actually see that there's a nice laminar flow here, as you can see, parallel lines coming out the top. And as it reaches a certain height, the draft in the room and a variety of other parameters, starting possibly the temperature changes and so on, tend to cause a chaotic movement, which is breaking into turbulence from a laminar pattern. If you keep watching this for a second, you'll see it very distinctly. We're beginning to get a laminar pattern growing up here, a couple of parallel lines, and then it just starts to bubble over and turn into a turbulent flow regime. So how can we predict this? I mean, basically, that's what I'm going to try and explain, how we predict the point where the flow changes from the nice parallel lines into a more turbulent flow. And we're going to relate what I'm talking about to actual drilling fluids rather than smoke and so on, but I'm putting the smoke up here to make it easier for you to visualize the difference between laminar and turbulent flow. So whichever flow model we're using, we need to work out whether the flow is turbulent or laminar to allow us to determine which equation to use. And why is that? Well, at low flow rates, the energy loss varied directly with the velocity of the fluid, as in 2 times the flow gave 2 times the pressure. I mentioned this in one of the other modules. And at high flow rates, the energy loss varied with the square of the velocity of the fluid. So 2 times the flow gave us 4 times the pressure. And the critical velocity is the fluid velocity at which flow changes from laminar to turbulent, the laminar to the turbulent regime. And the transition between laminar and turbulent, or L and T, as it's quite often noted on hydraulics reports and so on, the transition between L and T There's a single value in the Bingham model, and it's also a range of values in the power law model, or both power law models, so the power law and the yield power law. Now, just having a look at cartoon versions again of what the flow profiles actually look like. In a laminar flow, we've got basically parallel laminae, if you like, or parallel layers of fluid sliding past each other in nice straight lines. In turbulent flow, we've got fluid going in all directions. There's an overall fluid direction, and they're all moving up the pipe, in this case, or up the annulus in this case. But if you look at any individual molecule, it may well be moving even downwards in the opposite direction to the overall flow. So there's a more chaotic motion within turbulent flow. Just to explain it a little bit more, as the name suggests, it involves basically concentric layers or shear planes of mud flowing through the pipework with little intermixing of the layers. Now, if you imagine that this blue area is the blue cylinder is basically the borehole, and the green at the back is the inside of the borehole, and these grey cylinders, if you like, are is the mud. It's the concentric layers of mud. You can see that on the outside, the mud is actually pretty much stationary. It's touching the borehole wall, and on the inside, it's going much faster than the outer layers. If this was the inside of a pipe and there was laminar flow in it, if you have a look at the velocity profile, we'll show you with these arrows here. Basically, the fluid on the outside is going slower, and the closer to the center you go, the faster it's moving. So at any point within the overall continuum, if you looked at that point and looked at the flow profile or the velocity profile within it, you would see essentially like a parabolic shape with the fastest area in the center and the slowest areas on the outside. In fact, on the boundary layer at the contact point between the mud and the borehole wall, the actual fluid's stationary. Just looking at that in 2 dimensions this time instead of that 3-dimensional diagram, it's a parabolic flow profile with virtually stationary on the outside and the fastest areas in the center. Now, in laminar flow, fluid molecules basically move in straight parallel lines, and if you actually added a dye into that fluid that's in the laminar flow regime, the dye wouldn't actually mix into the water or the fluid. It would actually streak out in approximately a straight line. It would follow those laminae and not intermix between the layers of fluid. And laminar flow is characteristic of slow-moving, shallow water, and also flows where the fluid is very viscous, like glacial ice or mud flows that have very little water content. So you can see that it's dependent on the geometry, as in shallow water, and it's also dependent on the velocity, as in it's got to be quite slow. So it's going through a shallow area, and it's also dependent on the viscosity. So if you vary these things, you're going to vary the flow regime. Now, looking at the other flow regime, we've got, at the other end of the scale, we've basically got turbulent flow. And if you have a look at that same cutaway whole section here, you will actually see that overall there is an overall velocity going in this direction, but within that, the various molecules may all be tumbling around in random directions, basically producing a sort of chaotic cloud of molecules of particles as the overall flow profile moves up the wellbore. And as I said, in the inside of basically the overall flow will have a fairly constant velocity right to the outside, and then at the very outer layer it's going to be very, very low in basically laminar flow at the at the boundary layer on the outside of the fluid, just where it's touching the wellbore, and where it actually touches it's going to be actually static again. It's going to be not moving, but there's going to be laminar flow just in the first fraction of the wellbore, and then it becomes chaotic. And that fraction of the wellbore varies depending on the fluid properties, the roughness of the pipe, or the roughness of the rock and so on. So there's a variety of variables that will go into how thick that laminar layer is. If you imagine a turbulent flow comes up, it's still got a parabolic flow profile to a certain extent, in that the center is still going to be the fastest. But the fluid velocity towards the outside is not far removed from the fluid velocity on the inside. The whole thing's moving very uniformly, if you like, up there, apart from the boundary layer at the outside. Just looking at that in 2 dimensions again, you've got an overall velocity like that. You've got fairly constant frontier of flow profile here. It's nice and, well, nearly flat, but then as it comes to the edges of the flow, it rapidly drops off to laminar flow, and it's actually pretty much static at the edges, where it's touching the edges of the pipework or the borehole. So turbulent flow is characterized by complex motion of fluid molecules and particles within that fluid. And they move in all directions and bursts upwards, downwards, and forward motion, and even some backward motion. However, there is an overall direction, and that's in the flow direction. There is one overall direction that's governing the flow. And there's abundant mixing in the flow, and if you added dye to a turbulent fluid, it would mix into the fluid incredibly quickly. It would just, you drop your dye in, the whole thing would change color very, very rapidly as the flow progressed. Whereas with laminar flow, as I said, the dye would just streak out in a straight line. In turbulent flow, it starts mixing instantly. Now, most water and air flows are turbulent to some degree, and turbulence is very important for solids transport because it makes grains easier to transport and tends to keep them moving longer. It keeps them up in suspension a lot longer than if it's in laminar flow, usually because it's faster as well. But one of the downsides of turbulent flow is that it's highly erosive, and as it passes loose formations, it can cause large washouts as well. Okay, between laminar and turbulent flow, there's also a transitional zone, and as its name suggests, it's a transition zone between laminar and turbulent flow. Therefore, it's got a bit of both worlds going on in it. It's got some laminar flow throughout, and there will be some areas of turbulence within it. And this can, depending on the fluid properties, this transitional zone can be quite a wide zone, a wide variety of parameters, from the pure laminar flow to pure turbulent flow, or it can be quite small. But the important thing to note is that in this, there's some laminar flow, some turbulent flow, and when you're actually using equations to work out the pressure drop, when you've got laminar and turbulent flow going on in the same thing, it becomes very, very difficult to actually predict what the pressure drop will be between both regimes. It's easier to predict it in laminar flow or turbulent flow than it is to predict it in this transitional zone, because this can be flipping between a bit of quite turbulent flow to quite laminar quite quickly, and the pressure will be jumping quite significantly, because as I said before, you double the flow rate. In laminar flow, it doubles the pressure. If you double the flow rate in turbulent flow, it quadruples the pressure. So if you've got a bit of both going on and it's flipping between them, the pressures will be jumping up and down quite rapidly, and it will be difficult to predict. Now, in a concentric annulus, all regimes have a profile that is basically similar to a donut. You've got maximum velocity in the center, and towards the outside of the wellbore, it's lower velocity, and towards the pipe. In this case, let's just say the pipe's not rotating. The velocity towards the pipe will also be low. So you've got maximum velocity coming up here, represented by the red lines, and the more blue are lower velocities. And if you just look down on top of that, you've basically got something that's looking like a donut shape, the sort of thing that a cop would eat in his break time. But basically, you've got this kind of, this area here is the fastest velocity, and moving towards the outside or the inside, you've got much slower mud. So you've just got this donut. In a concentric annulus, you'll have a donut moving up the wellbore. In an eccentric annulus, the flow profile, you'll have much more of an exaggerated parabola on the top and much less of a parabola on the bottom, much lower rates on the bottom. The more eccentric the annulus gets. We'll see a bit more of that later on. Now, as I said, turbulence in the annulus can be quite destructive. If the flow is turbulent, erosion would likely occur across loose formations. So if you have a look at this, if you flip to turbulent flow by increasing the annular velocity or increasing one of the parameters that go into turbulent flow, I'll show you a few equations to show you what goes into turbulent flow. If you change it from laminar to turbulent, then this might happen. If you're going through a friable formation, you'll end up with a big washout in that area. And then if this was in an inclined wellbore, you could end up with a whole load of cuttings coming up here and going into a wider annulus where the actual flow rate reduces and the cuttings come out of suspension and start collecting in this area. So turbulent flow, although it's good for hole cleaning, it can also cause hole cleaning problems. You'll find that out later on as well. But it also creates a much higher pressure drop. So ECD and standpipe pressure increase, both increase much quicker once critical velocity is exceeded. And talking about critical velocity here, and that's basically, it's one of the parameters that go into turbulence. It's usually noted on a hydraulics report as you've got your annular velocity and a critical velocity, and when the annular velocity exceeds the critical velocity, that's you in turbulent flow. Critical velocity should be distinguished from critical flow rate, which is something I talk about when I'm talking about hole cleaning, just to make that distinction quite clear.